The last video ended on the note of trying to sketch polynomial graphs systematically. So I have decided to make this whole video about sketching graphs that way. So the introduction, um, when you sketch the graph of a polynomial function y equals f of x, you're not plotting every point, right? You're just sketching. So instead, we can analyze the algebraic form of f of x, extract structural information like degree and leading coefficients, roots and multiplicities, intercepts, and some key points. Okay, degree and leading coefficient, those already tell us some things. Then the roots and their multiplicities, they give us some information, and then the intercepts and some key points, like we considered in the previous video. So we can use this information to draw a rough but accurate shape. Finally, we can use technology to check how well we have been able to do those graphs. So the systematic procedure include determining degree and leading coefficients, which tell us about the end behavior. We've seen this a lot of times. And we can also find and classify roots with their multiplicities. We compute intercepts and some key points. Then we can draw a rough sketch through these points with proper shape. Then we can use technology to verify and refine. Okay, let's go for it. Degree and leading coefficients, of course, we've talked about this a couple of times, for several times for that matter. So um, step one is about degree and leading coefficient, and this tells us the end behavior of the curve. So let f of x be an x raised power n plus an minus 1 x raised power n minus 1 plus all of that plus a1x plus a naught, with an not equal to 0. So the degree is n, of course. That's the highest uh, exponent. The degree is then the highest power of x with non-zero coefficient. Then the leading coefficient is an. So the degree and this coefficient tell us a lot. So these two determine the end behavior of the graph of y equals f of x. So when we talk about even versus odd degree, if n is even, the two ends of the graph go in the same vertical direction. All right. The two ends of the graph go in the same vertical direction, either down or up, depending on the coefficient now. Then if n is odd, the two ends of the graph go in opposite vertical directions. So if one is going up, the other is going down in the other direction. Okay, so we also have signs of the okay, maybe very easy ways to go about this, right? I can just do simple one, x raised to power 2. Okay, now x raised to power 2. So you see the two ends going in the same direction. So for x raised to power 2, but for x raised to power 3, okay, so you see, okay, let me remove this so we can see that in full. So as this one is going up, this one is coming down. So that's what we mean by all this. So if n is even, the two ends of the graph go in the same direction, vertical direction. If n is odd, the two ends of the graph go in opposite vertical directions. So we talk about sign. The sign of the leading coefficient also has a determination in this. Okay. So combine the parity of n with the sign of an. So for even degree and an greater than 0, of course, for even degree, we already know that the two ends go in the same direction. So in this case now, as x approaches plus or minus infinity, then f of x will always go to positive infinity. Both ends are up. All right. That we're talking about positive coefficient of the highest power now, of the highest, the leading coefficient is positive. Then if we have even degree and an is less than 0, that is, it is negative. I think I demonstrated that the other time. So as x approaches plus or minus infinity, then f of x is equal to minus infinity, and both ends are down. Now look at this. Starting with x squared now. So this is x squared. So as goes towards infinity in the negative direction, and in the positive direction, you see the function goes towards a positive infinity in both directions. Okay, but if you put minus now, you see, as x goes to infinity in the right direction or in the opposite direction, you see the two of them go into negative infinity in the downwards direction. So that's the idea. Now we talk about odd degree. So if you have odd degree and the coefficient is greater than 0, so for odd degree, in that case, as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches positive infinity. Overall, bottom left to top right, like y equals x cubed. So we saw y equals x cubed the other time. Now let's see it again. So you see, as x is approaching infinity on the positive side, the function is approaching positive infinity like that. As x approaches negative infinity, the function approaches negative infinity. So in that case, for that. Okay, so for odd degree and an is less than 0, that is, it is negative. So as x approaches negative infinity, so you now have a reversal now. So negative leads to positive, positive leads to negative. So as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches negative infinity. Overall, we have top left to bottom right, like y equals minus x cubed. Okay, this now, so you have a flip over. All right, so as x approaches negative infinity, the function approaches positive infinity. As x approaches positive infinity, the function approaches negative infinity. Very important to understand that. So this gives the tails of the graph before you know any other details. So you can already know the tail of the graph depending on the degree and the leading coefficient. Okay. Now we talk about step 2, where we deal with roots or zeros and multiplicities. So to find the x-intercepts, we need to solve for f of x equals 0. We've done that a couple of times. So if possible, you can factor f of x into the form f of x equals an x minus r1 m raised by 1 raised by m1 rather, x minus r2 m raised by 2 all the way to x minus r raised by mk, where r1 to rk are the real roots, m1 to mk are the multiplicities, m1 plus all of this plus mk is less than or equal to n, which is the degree. So each real root ri corresponds to an x-intercept, ri, comma 0. We dealt with that in the last video. And we also talk about the effect of multiplicity on the graph. In fact, this has been dealt with a couple of times. So at a real root x equals r, if the multiplicity m is odd, the graph crosses the x-axis at x equals r. Okay? So, I mean, we did that in the last video, so I'll just go over this. So if the multiplicity m is even, okay, well, I think there's no crime trying to do this over and over again. So imagine that if you solve this, right, it gives you 0 3 times. That is odd, right? And okay, let me follow those things. So if the multiplicity m is odd, the graph crosses the x-axis at x equals r. So you see, so this one crosses. I think the easiest one is the simple one, x raised power 1. Okay, no, this doesn't work here. Okay, yeah, I think x raised power 3 is fine. X raised power 3. So, I mean, the x is equal to 0 3 times. So that's why you have this like relaxed kind of curve right here. Okay. And then if the multiplicity m is even, the graph touches the x-axis and turns back at x equals r. So imagine instead of x cubed, we now have x squared. So you see the solution is 0 twice. So it touches 0 and just bounces back instead of going to the other side, going to the negative side, you know. So for more detailed behavior, multiplicity 1 is just simple roots. So imagine multiplicity 1, x raised power 1. So it's just x is just equal to 0 or something like that. Y is equal to x. Or to make it make more sense, we have x minus 1. Okay, x minus 1. Okay, into x plus 1, right? So each of the solution to this expression will be 1 and minus 1 with multiplicity 1 each. So you see they cross the x-axis at those points. So for multiplicity 2, the graph looks parabolic near the roots. It will touch and bounce. I mean, we've done this a couple of times also. So x squared now. So x is equal to 1 with multiplicity 2. So that's why at x equals 1, so the graph touches the point and bounces back. But you still have this one of multiplicity 1. So that just crosses the x-axis at minus 1, like that. Then higher multiplicities. If you have odd multiplicity 3, 5, this still crosses but with a flatter shape near the axis, like y equals x cubed. Even multiplicity 4 over 6 touches and bounces with a flatter contact. So, I mean, the general behavior is this touching, right? So, but go beyond that, every other thing you have is flattening out. So let's say this is now power 3. So this one, multiplicity 2x equals 1 multiplicity 2. It touches and bounces back. All right. And then x plus 1 raised to power 3. Okay, so you have that smoothing thing going on there. So if I do this now and change the multiplicities to even bigger stuff, then you just have them flattening out. X minus 1 raised to power 4. So you see it flattens out instead of being sharp like this. Then this one is now 5. That 5 also, you also have the smoothing, flattening out like that. And that can keep going as much as you want. Okay, let me do one more. So now we have x raised to power x minus 1 raised to power 6 and x plus 1 raised to power 7. So it's just about flattening out over and over again like that. Okay, so with that out of place, let's talk about complex roots. For polynomials with real coefficients, complex or non-real roots occur in conjugate pairs. So complex root does not appear as x-intercepts on the real graph. So sometimes, and that's why in the last video we said that if you have a function, right? You are going to get uh at most, if the function is of degree n, you're going to get at most n complex roots. And knowing that real roots are subsets of complex roots now. So, and that's why sometimes even something with power 5, you may have just one root showing. It means that root, depending on the nature of the graph, that root showing maybe we have a multiplicity of more than one, or it has some real roots and some complex roots which will not appear on the curve, but they still count toward the total degree and reduce how many real intercepts you can have, right? So step 3 now, intercepts and some key points. In the last video, we talked about intercepts and turning points. So y-intercepts occurs when x is equal to 0, right? So when you have a function, just substitute x equals 0. Whatever you have left is your y-intercept. So y-intercept is simply f of 0. So the point is 0, comma f of 0. So for a polynomial, f of x equals a n x raised by n plus all of this up to a1x plus a naught. We have f of 0 is simply a naught because every other thing goes to 0. And that will be the constant term. So the constant term in any polynomial is your y-intercept, basically. So even without doing anything, just take the constant term out, and that's your y-intercept. So that is 0, comma that a naught. That's the point for the y-intercept. So for x-intercepts, you have to solve the function at 0. So in this case now, you have x-intercepts. So from the factorization of solving f of x equals 0, each real root r gives an x-intercept r, comma 0. From the multiplicity of r, you already know whether the graph crosses or just touches at that point. So it crosses for odd multiplicity and touches for even multiplicities. So additional key points to do here, to check. So to improve the accuracy of the sketch, choose some extra x values. So maybe just in between to just suit you. So pick values between consecutive real roots. Then optionally pick values beyond the outermost roots so you can see like extended behavior. Then for each chosen x, compute y equals f of x, plot the point x, comma f of x. This shows how high or low the graph goes beyond between roots. Then where turning point, local maxima, and local minima are likely located. Then for symmetry checks now, so look for symmetry for special symmetry. So if f of minus x is equal to f of x, then f is even, then the graph is symmetric about the y-axis, right? So for instance, a very good example of a symmetric curve is x squared, right? Of even power, so x raised to power 2. So you see it is symmetric about the y-axis, because here now, whether x is negative or positive, it is the same all the way. Okay, that's why we mean that if f of minus x is equal to f of x, then f is even. Okay, so this is an x squared is an even function now because it is symmetric about the y-axis. But then, if it's an odd function, so if f of minus x is equal to minus f of x, then f is odd. The graph is symmetric about the origin. And this is a very good case with x raised to power 3. Okay? So you see it is symmetric. Even x raised to power 23 mistakenly gives us the same thing. It is symmetric about the origin. Well, my intention was x raised to power 3. So you see, it's symmetric about the origin. So this goes up, this comes down symmetrically like that. So if you detect symmetry, you can sketch one part and reflect it very easily. So either way, so if once you get this part, and because you know the power is odd, it is symmetric about the origin. So this goes up and it comes with by the same measure. So you see the area carved out at the top is the area carved out down here because of symmetricity. So and the same applies for x squared. Okay. So once you know this is like this, so you know whatever it comes like this, it bounces back with the same. The area here is of course the area here before the axis and after the axis, basically. Okay. So step 4 now, we talk about rough sketch of the polynomial. So once you have got all the information in place, you can now combine all the information, draw axis and choose a scale. So mark the x and y axis with tick marks, then plot all intercepts. So plot each real root r, comma 0, plot the y-intercept 0, f of 0, if it is not already a root, then indicate n behavior. So use arrows on both ends according to degree n, even or odd, leading coefficient a n positive or negative, right? Then you can shape near each root. So for roots with odd multiplicity, draw the graph crossing the x-axis. For roots with even multiplicity, draw the graph touching and turning back. For higher multiplicities, make the graph flatter near the axis. Use additional key points. Use extra points to guide the height and position of bumps and valleys. Turning point check. A polynomial of degree n has at most n minus 1 turning point. So if your sketch shows more than n minus 1 local maxima or minima, adjust the shape. Then you can connect smoothly. Connect all points with smooth curves without sharp corners. Then respect the correct end behavior and behavior at each root. Okay, whether it's crossing or it's touching. So step 5, using technology to check. After making a hand-drawn sketch, use the technology to verify and refine. So possible tools, you can have graphing calculator, computer algebra system, CAS, graphing apps like Desmos. I've been using Desmos all the way. Then there's GeoGebra and so on. Then for programming, for example, you can use Python with plotting. Sometimes I use Python to plot. Then you can check end behavior. Does the graph go to plus infinity or minus infinity as expected? Intercepts. Are the x and y intercepts correct? Root behavior. Does the graph cross or bounce at each intercept as predicted by multiplicity? Then turning point. Are the number and approximate positions of maxima or minima consistent? Technology is there to check and deepen your understanding, not to replace the systematic method. So in case you don't have technology, you should be able to put this whole idea together to get rough sketches of graphs. So let's have a worked example talking about sketching f of x equals x cubed minus 4x. First of all, we sketch the graph of f of x equals x cubed minus 4x using the systematic method. Step 1, degree and leading coefficient. So we write the polynomial. If you write it properly, you get x cubed minus 4x. I mean, it's already written properly. So x cubed minus 4x is not like 1 x cubed minus 4x. So 1, of course, is greater than 0. So that means that we are going to have a local minimum in this case. So the graph is going to be open upwards because of this coefficient we have here, positive. So the degree n is 3, that is odd. That means that we are going to have a crossing, but because the degree is 3, we are going to have a flat kind of crossing. You can already begin to visualize that. Then you cannot talk about the end behavior because it is odd, right? As x approaches negative infinity, f of x approaches negative infinity, right? Then as x approaches positive infinity, f of x is going to also approach positive infinity, okay? So in fact, offhand, you can already know that the graph is going to be something. I mean, this may not be accurate, but I'm just trying to do the initial thinking. I know the graph is possibly going to be something in this format. So that's just an idea to start with. Okay. So the graph goes from bottom to top, from bottom left to top right overall. So you see, bottom, where is it now? Okay, hand sketch. So bottom left to top right. That's a rough idea of what we are going to get. So then since you have that idea, the next thing is we want to find the roots and the multiplicities. And to do that, we solve. So you have x squared minus 4x. That's x into x squared minus 4 equals x into x minus 2 into x plus 2. So we have real roots. X is equal to minus 2 multiplicity 1. X is equal to 0 multiplicity 3. X is equal to 2 multiplicity 1. All right. So in this case, now it means that this graph is going to touch the x-axis at all these points sharply. So minus 2, 0, 2. Okay. So beyond this first guess now, then I can go ahead and say, now we know minus 2. So I have something like this. This is not looking accurate, but I'll try. We are sketching, so not a problem. So this is, let's say this is -2, and this is 2. Of course, this is 0 now. So we know there are solutions that the roots are, okay, I guess I need to change this. Okay, let me just go. So you have roots here, 0, and -2, 0, and 2. Okay, so we have roots at those points. So we have that first of all. Then next, we so all multiplicity are odd. So the graph crosses the x-axis at -2, 0, and x equals 2. So, well, I mean, we can make bold to do this first of all. So you have crossing, crossing, crossing. Okay. So let's see how that's going to come up. Okay. Then we have intercepts and key points. So for the x-intercept from the factorization, we have -2, 0, 0, 0, 2, 0. Of course, those are the things I've indicated on the curve like this. -2, 0, 0, 0, and 2, 0. Okay. Then y-intercept, f of 0 equals 0. So the y-intercept is 0, 0. So the function doesn't have a constant term. So the intercept is still 0. So that's fine. We are still in order. That 0, 0 is what I already have in the center here, right? Then the next thing, so we can now have extra key points now. So at x equals -3, if you put -3 into the expression, f of -3 is -3 cubed minus 4 into -3. That's -27 plus 12, which is -15. So it means you have -3, comma -15. Okay, so that's -3. So this is 2, right? So let's say -3 is there. So we have -3 against, say, I just want to do this. Let's say this is 5, this is 10, and this is 15. So this is -3 -15. So we have this point right here. Okay. Then we try another point. So if you try -1, so, -3 is outside of -2, which we already have our solution. So that gives us the extremity of that. Then x equals -1. So if you put -1, you get 3. So that -1 against 3, -1 against 3. So let's say -1 is somewhere around here. So this is -1 against 3. 3 should be somewhere around this place. So we have this now. Okay. Then what else? We can try other extra points. At x equals 1, we have 1 cubed minus 4 into 1. 1 minus 4, that's -3. So 1 minus 3, right? 1, let's say this is 1 here, and we have -3. Okay, of course, this is 5, -10, and all that. So 1, that's minus. So 1 minus 3 can be somewhere here. Okay, we can try more points. So we have x is 3. That's 3 against 15. Okay. Okay. Yeah, I think this should be 3 against -15. Sorry, my bad, my bad, my bad. This is -15. So this should be 3 against -15 here, sorry. Then 3 against 15 now. Let's say this is 3, and then 3 against 15 up here. So take note of all the points now. So you see, with all of that in place, we can then join up beautifully. This shows the shape between and beyond the roots. So with this in place now, we can then join up. So we have this, and then this. So here we see like a maximum point around here. We have maximum point. That is -1, 0. And we have a minimum point here. This is okay, this is -1, 3, sorry. And we have a minimum point here. This is 1, -3. Okay? So that's what that sketch looks like. That's how it is like to sketch. So the rough sketch, finally, we see to sketch y equals x cubed minus 4x now. So plot the intercept, which we've done. Plot extra points, we've done that. Use end behavior. We've seen the end behaviors, right? So as x goes towards uh, positive infinity, the function goes towards positive infinity. As x goes towards negative infinity, the function goes towards negative infinity. Because the leading coefficient is actually positive, that's why we have that. Okay, I think this keeps coming in between, but it's okay. So then what we can use, okay, we've talked about the end behavior. Then we can now have the shape through points. So the curve rises from below, crosses at x equals -2, as you can see. So it rises from below, crosses at -2, goes up like this, comes here, turns over, and keeps going like that. Okay, so the curve rises from below, crosses at x equals -2. Okay, rises to -1, 3. That's the maximum point, as you can see. So it rises to -1, 3 here. Okay. Falls to cross at 0, 0. So it falls back at 0, 0 here, as you can see. Then continues from 1 to -3, continues down to minus 1 -3. That's the minimum point. Like I said, this is minimum point. So maximum point is -1, 3. Minimum point is 1, -3. Okay. So it continues there. Then rises to cross at 2, 0, which is another solution. So it rises to cross here at 2, 0, and it goes up like that, and beyond. So then the smooth curve connects all plotted points with a smooth cubic-like S curve. No sharp corners. Of course, mine seems to have some sharp corners, but it's because I find it difficult drawing that easily, but it's okay. So you just have the idea. So it has to be smooth, a smooth curve like that. So using all this information now, that's the plot. That's the systematic sketch of x cubed minus 4x. Then you can then check with technology. So using a graphing tool to plot y equals x cubed minus 4x and check. So at the okay, I mean, so we can go to the response x cubed minus 4x. X cubed minus 4x. Okay, that's really true, right? So we have the roots -2, 0, and 2 settled. Then, based on the extra things, we have minus minus 1.15. So it's technically -1, 3, right? And then we have this 1, -3, like that. So yeah, and so we say everything matches. So use the graphing tool to plot y equals x cubed minus 4x and check x-intercept at x equals -2, x equals 0, x equals 2, y-intercept at 0, 0. Overall cubic x shape from bottom left to top right. You can see bottom left to top right, like this. Okay. Then y-intercept at 0, 0, correct? Then, because the function doesn't have a constant. So overall cubic S shape from bottom left to bottom right. I've taken care of one local maximum between x -2 and 0 because there's a sign change there, right? X equals -2, x equals 0. So we have a local maximum right there. And then we have a local minimum between x equals 0 and x equals 2. That's this minimum point here, like that. And then, yeah. So if your hand sketch matches these features, you have successfully applied the systematic graph sketching method. And that's it right there. So before we go, I'm going to do this. I'm going to solve this first problem. So it says for the polynomial f of x equals 2x cubed minus 3x squared minus 8x plus 12. So state the degree and leading coefficient. A, we need the degree. We need the leading coefficient. That's the first part. The second part, describe the end behavior. Describe end behavior. Of course, end behavior is going to be determined by that leading coefficient and the degree. Then C, factor completely if possible, and find all real roots and multiplicities. Okay. D, find the y-intercept. Find y-intercept. That's the next thing there. Then finally, sketch the graph by using the systematic method and check with technology. Okay, sketch. That's the fifth thing we need to do. All right, so let's go ahead and do that here. So, so I go for this. So here now, f of x is equal to 2x cubed minus 3x squared minus 8x plus 12. And we need to sketch this, right? So first of all, what is the degree? The degree is 3. Then the leading coefficient, leading coefficient is 2. Okay? Now with that in place, we go for the next one. I mean, by the way, leading coefficient is 2. That means 2 is greater than 0, right? Because 2 is greater than 0, of course, we know that, and the degree is 3, and the leading coefficient is 2. So we know that in this case, um, as x goes towards positive infinity, f of x will also go towards positive infinity. Then as x goes towards negative infinity, f of x goes towards negative infinity. So that's like an idea. Okay. Oh, I'm already answering question 2. So let me just answer it the best way possible. Okay. I was jumping up ahead of myself. So B, we need to describe the end behavior, right? Okay. So end behavior, end behavior. End behavior tells you what happens at infinity. Now, because the degree is odd, right? Since n, since the degree, since the degree is 3, okay, as x approaches positive infinity, f of x also approaches positive infinity. So we know the curve, of course, is going to be something like from here to here. Okay? As x goes this way, this goes positive too. As x goes negative, this is positive infinity. This is positive infinity. This is negative infinity. So as this goes towards infinity, the function also goes in that direction, respectively. Okay? So as x goes towards negative infinity, f of x also goes towards negative infinity. That's talking about the end behavior. Okay, so we already have an idea of what the shape might look like. This may not be accurately the same, but for all we care, we know the graph will emerge from bottom left, and it will start from bottom left and get out at bottom right. So other things can happen in between, but at least we are persuaded about this for starters. So see now we now need to factor completely. To factor completely, okay, to factor completely. All right. So we need the factors. We need the factors of the leading coefficient, the factors of the leading coefficient. So the leading coefficient is actually it's actually 2. Or let's call that A3, that's the coefficient of x raised to power 3. That's A3, and that is 2 here. So the factors are plus or minus 1 and plus or minus 2. Okay? Then also we need the constant. We need the constant term. The constant term here, we can call it A naught. A naught now is 12, right? 12. So the factors of 12 will now be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay? These are the factors. So the possible rational roots, the possible rational roots are, the possible rational roots are, if you like, you can call it like this. All the collections of all the possible plus or minus a naught all over A3. Okay? That's like, so let's check them out now. A naught all over A3. That's like plus or minus 1 over plus or minus 1. That's plus or minus 1. Then plus or minus 1 over plus or minus 2. That's plus or minus 1 over 2. Then plus or minus 2 over plus or minus 1. That is plus or minus 2. Then plus or minus 2 over plus or minus 2. That's plus or minus 1 that you already have. Then plus or minus 3 over plus or minus 1. That is plus or minus 3. Then plus or minus 3 over plus or minus 2. That's plus or minus 3 over 2. Then plus or minus 4 over plus or minus 1. That is plus or minus 4. Okay. Then plus or minus 4 over plus or minus 2. That's already plus or minus 2. Then plus or minus 6 over plus or minus 1. That's plus or minus 6. Then plus or minus 6 over plus or minus 2. That's plus or minus 3, which we already have here. Then plus or minus 12 over plus or minus 1. That's plus or minus 12. Then okay, plus or minus 12 over plus or minus 2. That's plus or minus 6, which we already have. So these are possible rational roots. So the possible rational roots, so no solution here. No, so the solution to this, to the function is here. I mean, it has to lie here. Of course, we are expecting 3 solutions, and all the 3 must be one of these. So that's that. So since we have established that, we can then begin to factorize. You know, we have to factorize completely. So we now begin to try x equals 1, plus or minus 1. So try x equals 1. That means that f of 1 will be 2 into 1 cube minus 3 into 1 squared minus 8 into 1 plus 12. So that is 1 raised power 3 is 1 times 2, 2. 1 raised power 2 is 2 times 1 raised power 2 is 1 times 3, 3 minus 8 plus 12. Okay, so this is 2 minus 3, that's minus 1. Minus 1 plus minus 1 minus 8 minus 9 plus 12. That's plus 3. Okay, that's 3. Or 14 minus 11, that's 3. Sadly, 3 is not equal to 0. So x equals 1 is not a factor. I mean, is not a root, and x minus 1 is not. It's not a factor. It's not a factor of f of x. So we keep trying. Next, we try x equals minus 1. Okay, so that means f of minus 1 will be equal to 2 into minus 1 raised power 3 minus 3 into minus 1 raised power 2 minus 8 into minus 1 plus 12. Okay, so we have f of minus 1 now to be minus 1 raised power 3 is minus 1, so is minus 2. Minus 1 raised to power 2 is 1 times 3, that's minus 3. Minus 8 times minus 1, that's plus 8 plus 12. Sadly, no answer yet. This is 20 minus 5, that's 15. So 15 is not equal to 0 again. So x equals minus 1 is not a root. It's not a root. And x equals, and x plus 1 is not a factor, of f of x. So our search continues. So we know another possibility will be plus or minus half. But let's leave half alone and go for the whole numbers. All right? Because it might be difficult dealing with half. But it's not bad to try though. We try x equals 2 now. Try x equals 2. So that means f of 2 is 2 into 2 raised to power 3 minus 3 into 2 raised to power 2 minus 8 into 2 plus 12. So that means 2 raised to power 3 is 8 times 2, that's 16. So 2 raised to power 2 is 4 times 3, 12, minus 16 again, plus 12. Okay, this is looking great. So 16 cancels 16, minus 16, minus 12 cancels plus 12. So this is 0. So finally, we got something. So x equals 2 is a root, all right, and x minus 2 is a factor of 2x cubed minus 3x squared minus 8x plus 12. So now we have found, this is our polynomial p of p of x, if you like. And this is our divisor, d of x. Okay, so now we have found a factor. We are expecting 2 other factors if they exist. So what we are then going to do is to use all right, to find the other factors using synthetic division. We can also use long division, but synthetic division is fine because the divisor, d of x, is a linear expression, x minus 2, okay? So to find the other factors using synthetic division, okay, so we just have this. Then we have get the coefficients. For x cubed, we have 2. For x squared, we have minus 3. For x, we have minus 8. And then for the last one, I like to break this apart. We have 12. Because whatever we get here is going to tell us if it is really divisible or not. If you get 0 there, then it means it is divisible. If not, it's not. But we already know it is, by the way. So, and then at this side here, we are going to put this 2. Or if you equate x minus 2 to 0, you get 2. So that 2 now will be here. Okay? So for synthetic division, what do we do now? So we have so these 2, bring it down first of all. So you have 2 here. So then you now have this 2 times this 2, that is 4. Okay? So now minus 3 plus 4, that's 1. Okay? Next, you go for this. This 2 times 1 now. 2 times 1 is 2. You put it under the next coefficient. So minus 8 plus 2 is minus 6, right? So next, you have this. So let me go for this, okay? So this 2 now times minus 6, that's minus 12. Interestingly, 12 minus 12 is 0. So, but then the catch here is that this will give you a picture of the other factor. So minus 6 times x raised to power 0, 1 times x raised to power 1, 2 times x raised to power 2. So you can then say that, so other factor, the other factor is 2x squared plus x minus 6. 2 times x squared, 1 times x raised to power 1, minus 6 times x raised to power 0. So that's the other factor. And then f of x, which we started with, which is 2x cubed minus 3x squared minus 8x plus 12 is the same thing as f of x into, what did we get at first? X minus 2. That was the first factor. So we have x minus 2 into 2x squared plus x minus 6. 2x squared plus x minus 6, right? So we have f of x now equals x minus 2 into, we need two numbers to multiply to get 2 times minus 6. That is minus 12. And when we add, we get plus x. That's easily 4 and 3. 4 times 3 will give us 12, but we need negative. So it means one of them should have negative. But because we need positive in between, so the negative should go with the smaller number. So 4 minus 3 can be 1. So we have 2x squared plus 4x minus 3x minus 6. Like this. So we have f of x equals x minus 2 into, we can group now, 2x squared plus 4x minus 3x plus 6. So f of x is equal to x minus 2. Now we can factorize 2x into x plus 2 minus 3 into x plus 2. So we have f of x equals x minus 2 into x plus 2 into 2x minus 3. So we have factorized completely now. And then solving f of x equals 0 gives x minus 2 into x plus 2 into 2x minus 3 equals 0, such that if you equate each one to 0, x is equal to 2, x is equal to minus 2, x is equal to 3 over 2. So if you follow the trend, right? Therefore, you can say therefore x is equal to -2 or 3 over 2, that's 1.5, or 2. And those are we saw all these possibilities. -2 and 2, then 3 over 2. We saw all these possibilities, you know. We have minus plus or -2, and then we have plus 3 over 2. We saw all of those possibilities when we started out. Okay. So with this in place now, um we have got all the solutions. So we already know that if we sketch our curve. Okay, well, let's continue because we are still going to come back to this, right? So D now, to find the y-intercept, that's pretty easy to do. To find the y-intercept, okay, we have f of x equals 2x squared, 2x cubed rather, 2x cubed minus 3x squared minus 8x plus 12. So for y-intercept, f of 0, y-intercept, or can I just say y-intercept, the y-intercept occurs at f of 0. Okay, so f of 0 now is equal to 2 into 0 cubed, 3 into 0 squared, minus 8 into 0 plus 12. I don't necessarily don't have to do this because we know the y-intercept is simply the constant. So f of 0 is 12. Okay, so the y-intercept is 12. Occurring at x comma y equals 0 comma 12, basically. Okay, so with all this information in place now, we can already try to sketch our curve. So let's try to sketch now. Okay, let me go for this time around. So we have this, and we know there are three possibilities: -2, 3 over 2, and 2. Okay, so let's say this is 1, 2, 3. That's minus. Then here we have 1, 2, 3 on the positive side. This is the origin 0 right here. Okay, so we know the three solutions. The three solutions are -2, then minus. So we have -2, 1.5. Okay, this is 1.5 right here. -2, 1.5, and of course we have 2. This is here. So with that in place now, we already know the intercept is also 0 comma 12. So 0 comma 12, that's 12 on the y-axis. So this is x-axis. Okay, so let's say this is 12, right? Say this is, let me see, which is the easiest way to go now. Okay, let's just say this is 5, this is 10, and this is 15. It's a rough sketch. So let's say 12 is somewhere around here. Let's say 12 is somewhere around here. Okay, we already know that at the extremes, right? As this goes to the negative, the graph continues down there. Okay, so now the question is, and these roots they have multiplicity of 1 each. So the graph just cuts at those points, basically. So maybe one thing we can then do is we can get extra points. So we can get extra point at f equals -1. So at x equals -1, for instance, I think we did something like this before. We can just borrow from what we did. At x equals -1, we know that the result is 15. At x equals -1, okay? We have -15. So we can easily use that so that's x equals 1, right? x equals Okay, we can, in fact, we can use all these things we've done in the past. This is helpful. At x equals 1, you know, the function is 3. So we have 1 comma 3 that at x equals minus 1, we got minus 15. So that's minus 1 comma 15. So since we did this before, there's no point trying to do it over. Then, okay, we already got 2 at 0. So we are, at least we have extra point 1 comma 3 and minus 1 comma 15. So let's go for those. So we have now 1 comma 3. So this 1 now, comma 3. So let's say 3 is somewhere around here. 1 comma 3. And then we have minus 1 comma 15. So let's say again, this is, so for 15 now, this is minus 5, minus 10, and say minus 15. So minus 1 comma 15 will be somewhere around here. Okay. So somewhere around here. Minus 1 comma 15. So what else do we need? Okay, I guess we need minus 3 also. Okay, so that we can know some extra. So we can, let's do 3 and minus 3, so we can know what happens at the extremities. Because now it's a bit difficult to still get what the clear picture looks like. Okay. Uh Sorry. I wonder why I keep making this mistake. Okay. So it's minus 1 comma 15. That's a big issue. It's minus 1 comma 15, minus 1 comma 15. This thing. This right here, minus 1 comma 15. Okay, I think the picture is a bit clearer now because the other one was a bit confusing. That's fine. So I think with this, we now need, let's get some extremities. We need minus 3 and 3. So if we do this, 2 into minus 3 cubed, minus 3 into, okay, since this is extra, right? So let's say 2 into minus 3 cubed, 3 into minus 3 squared, minus 8 into minus 3 plus 12. So that's like minus 27. That's minus 54. Then this is 9 times minus, that's minus 27. Okay, that's plenty plus 24 plus 12. Okay. All right. This is minus 81 plus 36. So that's like that should be minus 45, I guess. Yeah. Minus 45. 45, yeah. Minus 45. That's a lot. Okay. So that'll be somewhere down here. Somewhere down here. So let's say it's somewhere here. So I have this point down here, like minus 45. Then for 3 now, so we can just change this to 3. This one changes to 3. So we have 54, still minus 27. Then this is minus 24 now. This is now minus 24 plus 12. So, and then we have 54 minus 27. That's 27. 27 minus 24. That's 3 plus 12, 15. So that means we have 3 against 15. So we have 15 here again. Okay, so now we have a clear picture of what is happening. So now we can join up the lines. Never mind, it's a sketch, so it can look somehow. So we have this. It should go smoothly normally. Okay, now I think it would have been good to, because it is, the multiplicity is 1. So we need it has to cross the line. Okay. That's where all the information become useful again. So one of the solutions is 1 over 1.5, that's 3 over 2. So it has to cross because the multiplicity is 1. So it has to cross and then it goes back like this. So this is what the sketch looks like. Okay, I guess I need to shrink it so we can see it at once. So this, so this is what that looks like. So the final thing we need to do is to now use we can use technology, like checking in decimals. I particularly want to be sure of I want to be sure of this crossing over. Of course, I'm sure since it is one multiplicity, it has to cross over. So this is what the graph looks like actually. So I'll come here now and check that up from here. So I have 2x raised to power 3. Okay, 2x raised to power 3 minus 3x raised to power 2 minus 8x plus 12. Okay. Yeah, so I think it's good. So here, the peak is this like 15. So the peak is that 15 point something, just like what I have. So 15, around 15 here. So that works. Then of course the 3 points of intersection minus 2, 2, and 1.5. Of course, the crossing over, I'm correct with the crossing over because the multiplicity is 1. And the minimum point here is like I think it's roughly 1.75 something something. Okay, so I didn't bother about that actually. Yeah, so that's about it. That's about it right there. Okay, so you want to try out these other questions as much as possible. I'll just flash them across the screen. Try your hands on them to see how well you've mastered uh, what I've been talking about, systematic sketching of curves. Of course, if you check under the basic calculus playlist, there's a way you can also use derivative to get the maximum and minimum points. So, but for polynomials, we're not going the calculus way now. So, but I mean, you can check the points in between. So try this out. Yeah, thank you so much for listening. This has been a very long one, but I think it's worth it. So in case you don't have technology, at least you can use all the information you have about a polynomial to get its curve sketched systematically. Thank you so much for listening. Um, if you have subscribed already, I thank you very much. Let me know what else you may need from this kind of thing. So if you have subscribed already, I thank you. If you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join, and that comes with some special privileges. Ultimately, comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.